We're now going to start session 2, where we're going to be thinking from a much more singular habitat perspective. I'm really pleased to be chairing this session. We have 4 fantastic speakers, each of them representing a different critical coastal habitat. And we're going to hear perspectives from each of them in turn. Our first talk is from Professor Iris Möller, who is at Trinity College Dublin. Unfortunately, she's not able to join us today, but she has sent her pre-recorded presentation, and she is watching online and is available for questions. That said, her talk is long enough that there won't be any time for questions, I'm very sorry to say. But please do take note of her email address. Please do send her emails. She's fantastic. She's going to be presenting the kind of physical geography perspective to salt marshes. So thank you, Iris.
Hi everybody, and it's wonderful to be able to give you a presentation today, and I'm sorry I'm not there in person. I'm based over in Dublin, and it would have involved a lot of CO2 emissions for me to come over in the time frame I had available, so I hope you'll forgive me for that. As I'm not there today, just a few links here on this website, on this slide. There's my email address. Please reach out to me if you have any questions after the presentation. There's also the address of the Rewrite project, rewriteproject.eu, and then the Naturescapes project at the bottom of the slide, and the catchment-based approach.org organisation, where one of the handbooks that I have recently been involved with on salt marsh restoration is published. And also, as part of this presentation, I was inspired by some of the discussions that go all the way back to the Managing the Land in a Changing Climate report that was written by the Adaptation Subcommittee in the UK. And discussions have also informed this presentation in my Nature Plus group here in Trinity, and the Climate Co-Centre for Climate Biodiversity and Water, which is a cross-jurisdictional UK and Ireland research centre that I'm quite excited about, that has recently started out with the lead here in Dublin. So I want to talk to you a little bit about my emphasis in my research over the last few decades on making space for functioning coastal wetlands. And really the effort to do that is motivated by the fact that a lot of coastal wetlands have been lost over recent centuries, that coastal wetlands are really important as carbon sequestration areas, that they support a lot of biodiversity, and you all know that, I'm sure, and that they support a lot of people through either their direct link to offshore fisheries, as the direct link to the marine, and they also provide a service landward in terms of providing flood and erosion protection. And there's also a link there to a website that you can find some more information on some of the exciting work that I've done with others in the European Union on the experimentation and providing evidence for salt marshes as coastal protection elements around our shores. So the big question that you start to ask when you work on coastal wetlands is really, where is the landward limit of the coast? Because coastal wetland consist of salt-tolerant plants, but they are terrestrial plants. So you're kind of really in this buffer zone between the land and the sea. And of course, at the seaward side, you ask the question, where does the coast stop and the marine start? Because actually coastal wetlands are really important, for example, as nursery grounds for offshore fisheries. And this is, of course, an image of Venice Lagoon in Italy, where you can really see this transition all the way from the uplands in the top left to the marine in the bottom right. The coast is really a connecting zone, therefore, and we are very aware, in all of us who are researching coastal ecosystems and coastal landforms, of their interdependent nature, the fact that they are very complex in this intertidal space, that they are open systems with inputs of energy and matter and outputs of energy and matter across boundaries that are difficult to define. They are extremely dynamic systems with sporadic, unpredictable events, for example, causing overwash deposits, as here on the island of Scald Head in Norfolk. And we really need to kind of think about these physical impacts on the coastal space in order to understand the coastal ecosystems and in order to achieve sustainable and workable seascape restoration. I want to draw your attention to the fact that meteorologically these environments are really driven by unpredictable factors. We don't know what the weather is going to be like in a couple of weeks' time. This is an inherent unpredictability, and this transition from the marine to the terrestrial that's illustrated in this diagram needs to be viewed in that context. So while we have the tidal datums here to define where the water level sits, we continuously have a fluctuation around that through meteorological conditions. Air pressure, wind directions generate water levels at different heights relative to predicted tides, and the waves, of course, on top of that are highly unpredictable. And the existence of our coastal ecosystems, certainly in the upper intertidal space where we get salt marshes, mangroves and so on, is really mediated by the fact that you have the foreshore across which the energy, the physical energy of the water is dissipated and modified. And if we don't consider the connectivity between the terrestrial and the marine in terms of the functioning of the coastal ecosystems we're concerned about, then we're missing a fundamental component that we need for their successful restoration. Sea level rise, of course, adds another dimension to this, because when we raise the sea level, then we raise the reach of the waves, if you like, onto the bed over which they propagate. Waves break when their height exceeds 0.78 of the water depth, roughly, as a rule of thumb. And so if the deeper the water gets, the more inshore the waves will break, and therefore the less dissipation of the waves' energy we're going to see before they interface with the coastal wetland ecosystem. All of that affects the transfer of sediment, the transfer of nutrients to and from the coastal ecosystem and the marine. We, of course, have big questions around sediment delivery into this space from the offshore, where we have offshore wind farm developments, we have dredging of river channels and so on. And then, of course, human actions on the terrestrial side can fundamentally affect sediment delivery via rivers and all sorts of other impacts. So the key question is in the context of what I would call concreted coasts, and this is a lovely image that I keep showing in presentations because it illustrates the trajectory we've been on so well, where in Cartagena here in Colombia in 1945 we had a very mobile sand spit, not dissimilar to the image I showed you earlier of Scoiled Head Island, and you can see how it became concreted between then and 2006, and apparently I'm told it's now even worse. So what does ecosystem restoration mean in the context of this trajectory over recent decades? How do we restore coastal ecosystems in this context? And I wanted to give you a glimpse of some of these challenges by bringing you all the way over here to Dublin, where you can see the current city and its close connection to the coast and to the marine, and the urban environments here very, very closely positioned to the sea, not least because of that kind of edgy outcrop that you can see on the right-hand side of the city, which is Dublin Port, and which is all built on reclaimed land. Now, it wasn't always like that. It wasn't always this urban. And if we go back to the 1720s on the left-hand side of the image there, we can in fact see the city located much further inland, and wisely so by the early settlers of Dublin. The bay itself was consistent of very mobile silts, clays and sands that would have shifted over time with the river channel shifting, and we can see that as we go through historical map evidence. But we end up on the right-hand side where you can just about make out the attempt to construct some training walls on the River Liffey, in the main channel of the Liffey, to keep it in place and stop it from shifting around in order to facilitate better shipping traffic and therefore commerce and economic activity into Dublin Port. So we kind of have known as society that naturally evolved coasts fulfill a function for us. The high risk zone can be a little bit further back when we have a naturally involved coast in front of us, and the early settlers of Dublin Bay clearly knew that. What can clearly happen in that kind of situation is that when we have sea level rise, we can see the migration of these dynamic spaces upwards and landwards, and if the high risk zone is located further back, then we're okay with that adaptation and that naturally inherent ability of the coast to adapt. Now the problem, of course, we have is that we have not taken that trajectory. We've built closer and closer to the coast, and we could see that in the case of Dublin. We need increasingly large interventions, and we have an increasingly larger, riskier development happening landward of those. And now we are clearly looking at what we can do in order to backtrack from that, and looking at hybrid interventions where we set back our sea defences slightly. Now, in the situation of Dublin, that's clearly really difficult, but it's interesting to look at the remnants of these adaptable spaces that we have here. And just for the Bay of Dublin Bay, we have two particular areas in the north and in the south that currently are providing coastal wetlands space to exist. And the interesting question is, of course, how can we keep those wetlands there in order to act as these beneficial spaces for us from all these different perspectives, not least the flood and erosion risk protective function. And we need to really see these environments in the context of all these physical factors that determine the deposition of sediments there, that determine the likelihood and the frequency with which waves or high energy wave events might affect the deposition of sediment there. And so you can see a windrose there. Of course, in Dublin Bay, we are fortunate in that the winds blow primarily offshore, but on the odd occasion we can get very strong winds from the offshore. So the big question is, how does this environment change in the context of these hard structures on the landward side? And of course, when we want to restore wetlands, we have to really ask ourselves at what scale are we actually restoring them at. And in Dublin Bay, there is no way that we should look at any smaller scale than the bay itself, because sediment, nutrients, waters are exchanged across the whole of the bay. So we have to have a landscape scale approach. And it's really important that we are aware of that kind of where we draw the lines of our scale, where our seascape stops and starts, is inherently linked to the time scale over which we look at that. So when I talk about the fact that we need to look at the whole of Dublin Bay in terms of our restoration approaches, we really need that scale, because we know that over the time scale of decades, there is very little sediment exchanged either side of Dublin Bay with the adjacent coasts. But over much longer time scales, we might have tectonism, we might have eustatic sea level rise, we might have ocean circulation changes and so on, as you can see in the top part of this diagram, that reach well beyond the decadal timescale. And of course we have also evolutionary change to the plants and the vegetation and the species that exist in that space that reach to geological timescales. So as a coastal geomorphologist, how I would see the restoration of the coastal seascape is really in the context of a framework that puts together the spatial scale on the x-axis here and the time scale on the y-axis. So if we are talking about ecology and ecological processes, we're right in the middle of this time scale here, perhaps thinking about decades and the spatial scale of maybe hundreds of meters to a kilometer. But actually we're needing to take into account scales and processes that happen on either side of that. And we really can't do ecological restoration without being very cognizant of the physical processes at much longer timescales. And we can return back to Dublin Bay here in this context, because clearly through our human existence over centuries and decades, we have put boundaries in place where there didn't used to be any. and we have disrupted the physical processes that then connect with our ecology. And this has been no different in Dublin Bay, where the construction of the southern and the northern training wall of the River Liffey have led to changes in the sedimentology. And as you can see there in the circled area to the north of the North Liffey's training wall, we've seen an accumulation of sediment that's led to a wide beach, dunes, and a salt marsh environment. And in that space, the question then is, how have we changed the ecology on the back of this? And we've now instrumented this area with water level gauges, and we are looking at the degree to which north and south of this causeway that you can see in the right-hand image there, we see a changed process environment that will change it's in the process of changing the ecology of the coastal wetlands, and it'll also change the future responses of those coastal wetlands to sea level rise. And all of this really requires a seascape approach to tease out what the important processes are. And you can read up more about that in our paper here in the Coastal Futures Journal. But what we've done is looked at the deposition rates of sediments on the salt marshes either side of the causeway by way of using accretion markers, which you can see in the left-hand side of the image here, and then also sedimentation elevation tables, which allow us to find out that salt marshes respond differently in terms of their elevation change on account of these kinds of disruptions, in this case the building of the causeway, and so they may lose their resilience to respond to a rise in sea level on account of those kinds of interventions. So it's these processes here, tides, sediment transport, and vegetation growth, that affect the next level up, the surface elevation change, the response to sea level, and the resilience of the system. And in our case, we find a different process environment on either side of the causeway that leads to very different accretion and very different elevation change. And again, if you want to look up the details here, I will refer you to that Coastal Futures paper. So a connected system became disconnected, and on the back of that disconnection, we now are faced with the challenge of teasing out how these landscape scale changes that are important over the decades and centuries that we need to think about with coastal restoration efforts and restoring the seascape, how they hang together and how the physical processes interact with the ecological responses. And of course, it requires reconnecting some of those disconnected systems. And I know that several of you are probably aware of the managed realignment sites around the UK. This is just the example of Freeston Shores here on the Lincolnshire coastline, where I've worked for many years before I moved over to Dublin. And the breaching of the seawall there in 2002, creating a 78-hectare coastal wetland on a space that used to be coastal wetland, was then embanked, disconnected if you like, from the seascape, and is now returned to it after being used agriculturally. The modifications of breaching this and reconnecting the space led to some unexpected side effects where the creeks seaward of the breaches were eroding and releasing a lot of sediment, which then affected some of the oyster beds in the wash embayment and so on. So we really need to be mindful of all these physical connections that affect the ecology. And we know now quite a lot more than we did many decades ago. We know that reconnected coasts, for example, reduce flood and erosion risk further landwards. So we've kind of started to establish some of this connectivity at the landscape scale between a reconnected coastal space and the benefits we have landward of that, by the fact that we can move people back to reduce risk further, and we can have early evacuation, early warning systems, evacuation plans, and so on. So there are lots of social responses that can follow from that connect the coast further landwards. But this reconnecting of the coastal zone to the physical process space is really critical as one of the elements. And of course, reconnecting the coast in terms of its natural functioning to what it once was in some shape or form also does much more. It addresses a lot of the sustainable development goals. It helps maintain the connectivity between land and sea, which reduces pollution prevents the kinds of effects you can see in the top left there, where people build too close to the shore and then experience the negative implications of that with increased erosion and then all of the health and well-being impacts of that. By reconnecting the spaces, we might help the poorest communities who suffer these kinds of impacts rebuild a better life, basically, and mitigate against those kinds of impacts. We might help maintain threatened livelihoods that might have been more attuned to the natural functioning of the coast, the harvesting of wild goods, for example, within coastal wetland systems in a sustainable way. And we might create new ways of benefiting in terms of livelihoods from these spaces. So, for example, new ways of doing aquaculture that is more sustainable than the full embankment and translation of coastal space into terrestrial agriculture. We might enhance health and well-being in the process, teach respect for dynamic nature, and encourage more sustainable industries and the economy. So all in all, coastal seascapes really require us to look beyond the dykes in both directions, because we need to link the physical to the biological processes. We really need to bring in biogeomorphology into the ecology. We need to accept the fact that coasts are complicated and dynamic and unpredictable, and the only way in which we can cope with that is by reconnecting to make the natural processes function in the way that they would naturally do and build natural resilience. That de-escalates risk and costs and builds a better future for people, biodiversity and climate, and it makes absolute financial and economic sense. So thanks very much for listening, and I look forward to the questions.
Thank you very much, Iris, for that really interesting talk. Please do take her up on that offer. Please do email her if you have any questions, if you want to follow up on any of the themes she's brought through. I thought it was fantastic to hear that perspective, also from the landscape, from the physical morphological side. I can't say that. But I'd like to bring us back into the room and back offshore a little bit to Ray Ward from Queen Mary University, who's going to talk to us about kelp.
Excellent, cheers. I'm not just talking on behalf of myself, I'm talking on behalf of the whole kind of recovery project. So there's loads of people and there's loads of different aspects of this research. So if there's any questions, there's Alice also in the crowd there, and Sam Fanshawe from Blue Marine. So maybe they might be able to answer some of the questions if I can't. So this is, I'm talking on behalf of the Sussex Kelp Recovery Project. This is the UK's largest marine rewilding project. So that's 304 kilometre scale. Good, decent, big. That's what we were talking about earlier. We've kind of said it's an ambitious and pioneering nature-based solution to restore our coastal ecosystems for biodiversity. Sorry, Teams is popping up here at the moment. For biodiversity, communities and climate. I think that's important that we're taking into account the fact that we've got communities, we're involving our local communities, as well as kind of looking at biodiversity uplift in this rewilding project, as well as kind of climate mitigation from a blue carbon perspective, which you heard about earlier. There's loads of people that are involved and loads of institutions, so you can see them all there, and they'll be coming up at the end as well. It's not. That's that one there. Oh, it's not working either now. Hang on. Maybe I just need to do that. Okay, that's working. I think it was just because Teams came in. Okay, so I've been involved in this for quite a long time. It was kind of initial discussions that we had about 2010 with Sussex IFCA, where we started to look and think, hang on, we haven't actually got any of the kelp that we've historically had along the Sussex coastline. So Sussex IFCA then pushed forward to get this protection for our nearshore coastal kind of ecosystems, and they developed this nearshore no trawling bylaw. Yeah, so it covers that huge area, and that was 4 years ago. So we've had 4 years of protection, so where we've kind of had passive restoration in place. We've got a range of different ecological monitoring methods that we're using to look at how the coastal ecosystem is actually developing to this protection from trawling, including putting in those turbidity sensors in the water to get an idea if that's changed over time, because historically we've had quite a lot of sediment in our water column. We've also been looking at catch data from IFCA, looking at eDNA analysis in the water column, as well as eDNA analysis in the sediments to have a look at changes over time, and eDNA on these autonomous reef monitoring systems. We've got divers going out, commercial divers. We've got research divers, and then we've got a load of kind of volunteer divers covering the whole of that area to get an idea of where are areas that we could potentially be looking at, because it's such a large scale. We've got the towed benthic video surveys, which I'll talk about in a minute, some potting surveys, baited, that's spelt wrong, I think that might have been voice to text, but that's not baited remove, that's baited remote underwater video surveys. We've been doing some genetic assessment of the kelp to get an idea of the specific genotypic markers within the kelp in the area. And then we've got turbidity sensors that we've got in the kelp zone. So the monitoring that's been going on for a very long time is in these kind of areas. So you can see that area that's in the kind of cross-hatching, that's the trawler exclusion zone that we've had for the last 4 years. And those points are where we've been dropping the bruvs over and also doing the towed video transects. And you can see that's overlaid with where the historic kelp beds were. So this is sort of 1987. So 1987 was that big kind of turning point for kelp when we had the big storm come through on the south coast. Okay, so you can see there are some areas where there was very, very dense kelp, some areas where it's slightly less dense, and then other areas where there was no kelp, particularly around kind of Littlehampton and the Ada estuary, where you've got rivers coming out and a lot of kind of high turbidity. So the bruv data that's been collected, that's been done off the back of the Sussex IFCA boat together with ZSL. They've been analysing that. And what they've been doing is they've been looking at various different species that are captured in there, but predominantly a habitat analysis, okay, and getting an idea of how that changes, because obviously we've got change as a result of that protection, but we also have kind of year-on-year changes. So we've been looking at how that's been changing those benthic habitats. The bruvs have been dropped over. That's that's a monitoring that's undertaken by University of Sussex. Alice has kind of been running that for the last few years. They've been dropping off these bruvs and leaving them in for an hour and recording what species are recorded in those areas over time. Okay, and then we've got the carbon work. That's kind of the stuff that I'm leading on, but together with Ian Hendy from the University of Portsmouth, ZSL and University of Brighton. And that's where we're kind of diving down. We've got 60 cores that we've been collecting from the offshore zone, down from about 20 metres deep to about 65 metres. Can't get any deeper unless you dig a big hole, but that kind of goes out quite a long way. So we're looking at that kind of deeper water carbon storage, and we're looking at changes in soil organic matter, how much carbonate material is in there, how that's influenced by particle size, because that varies quite substantially over the area. We're using radionuclide dating so we can get an idea of changes over time. Stable isotope analysis to get an idea of potential kind of carbon sources. And we're also doing eDNA analysis to get an idea of specific kind of contributors, particularly kind of kelp. And then there's the eDNA analysis that Alice is doing for her PhD, and she's been looking at kind of changes over time of what kind of species you find. That's what the water column work that she's doing there. And then we've also been dropping these arms off, not like arms, but these autonomous reef monitoring structures. Okay, so essentially they're like, imagine a load of plates that are bolted together. Anyone who's here in ZSL, you've got them. That's where we've been using them from. And what we left them in the water for about a year, and then we got an idea of what had actually settled in those plates, both above and below, in between those different sections. We took like really high resolution photos, get an idea of what had settled there, both the errant and sessile species, and we also did eDNA analysis of what was found there. Actually, it's very, very surprising that we had one of the highest biodiversity records in those arms that are found in kind of temperate ecosystems. Really, really good. And we picked up a lot more in the eDNA there than was found in your water stuff. That was quite interesting. Then we've also been doing some work with remote sensing, so to get an idea of changes over time. That's particularly kind of University of Sussex together with ZSL, Chris Jessen at ZSL, and to look at particularly at those kind of shallow subtidal and intertidal kelp. And we have actually found that in some of the areas in the intertidal, we've actually found kind of losses of the kelp. But in some of the other areas, there have been other changes. Then we've got Marianne Glascott from University of Sussex, who's been doing a lot of work with looking at sediment changes across the whole system. Sediment's kind of a bit of a limiting factor in Sussex for kelp. Usually when you think of kelp, you think of those beautiful kind of clear waters like you've got in down in the West Country. It's not quite the same in Sussex, and so Marianne's been looking at kind of changes and how that varies both temporally and spatially across that protected area, and also putting kind of sensors in there, particularly some kind of sondes in the water to have a look at kind of light availability in the kelp zone. We've also been doing a lot of work with our local kind of citizen scientists. If anyone lives in Sussex and they kind of wander along the coast, Sussex Wildlife Trust have set up this really good system where you can record kelp. And we've had quite a lot of our kind of local community involved in that, taking photos, recording where things are located, and then actually uploading it. So that's been really useful, because while I say we've got a wide range of groups that are involved in this research, we can't be everywhere across that huge area at all times. However, the local community can be, okay? So beyond that, we work quite closely with Sussex Underwater, which is an excellent group of kind of community volunteers that spend a lot of time underwater. They almost live underwater. I think they have some kind of marine adaptation. I do go out with them quite a lot. and what they've been doing is they're free divers and also divers from other kind of local groups in the area and shore wanderers. They're constantly in contact with us. Yeah, so they'll be emailing us. We've found this information. We found this kelp. We've just last year they identified that we had a huge load of stingrays that come in, which is the first time that we'd seen those in decades. And I think that's been a real positive to engage the communities, to get them involved so that they can actually say to us, maybe you should focus on this area, because sometimes we don't know. You know, we've got our specific areas where we're doing our research, but they can cover a much wider area. And we've got the main kind of SKRP partners, but we work with a wide range of other people as well, including kind of University of Sussex, University of Portsmouth, University of Bryan, Sussex Underwater, Big Wave Productions. Big shout out to those guys, because without their help kind of really raising the profile, it really did help kind of getting that protection of our coastal ecosystems in place. And then University of Exeter MCS. And hopefully I'll finish well in time and I've got time for questions.
Thank you for that incredible
I don't know how quick
And you get a prize for actually having... Yeah, don't have questions. So questions are also open to those who are online. But are there any questions from the room? Would you like to field them yourself?
Unless it's something that Alice or Sam can answer better, then yes.
Hi, I'm Fiona Mitchell-Langford from Campaign for National Parks and Marine Conservation Society. I just wondered whether you had any ambitions for the future of the project. Like, where is it going next?
I mean, we're constantly doing our monitoring. That it takes up so much of our time. We've also got the additional kind of research work. I think we're just about to put in a load more arms. So that's kind of part of what we're doing. We've got the ongoing monitoring that University of Sussex is doing. That we're constantly doing. We have got a few ideas. Well, no, we've got a lot of ideas of things that we'd like to do. And I think we would like to get an idea of kind of how actually some of those kelp are responding to the current conditions. So kind of, what are the growth rates under different conditions, particularly kind of changes in temperature, changes in turbidity. That would be really useful. And also maybe kind of trialing some kind of restoration. We've just to see if we need it. In addition to that, we've not necessarily SKRP, but there are other groups that that a range of us are involved in that have just dropped some kind of concrete habitats in the water. If you want to have a look at them, there's Sussex Underwater have done a really good kind of video of that. And essentially it's a 3.5 ton block with loads of kind of holes in it. And that was put in place to kind of promote particularly kind of cuttlefish, squid, edible crab and lobster kind of to colonise. That was last week we did that, and I suspect there will be something in there. As I was leaving there was a cat shark going in. It was pretty quick, so colonisation will probably be fairly rapid, I think. Don't know. Any other questions?
I'm really interested in, I don't know if you have the results yet, but the eDNA, if you're starting to see a shift in biodiversity post-trawling ban, and or what scales you think you might start to see those shifts?
Yeah.
I don't know if you're getting any resolution yet.
It's interesting. Alice can answer specifically for the eDNA, but we've seen changes, and the eDNA with the arms isn't quite the same as eDNA from the water, and it's not quite the same as we've seen from our kind of local teams. Alice, do you want to say about the eDNA specifically? Because that is 100% your work.
We're seeing slight shifts year on year, but I think, it's still too early to say if it's really linked to the bylaw. I think we just need longer monitoring to really know. But I'm analysing the 4th year's data at the moment. So also haven't done all the analysis yet. But slight shifts, not necessarily towards a more kelp habitat, because we've got control zones that we're comparing to, but maybe other things will colonise first and change, and then maybe the kelp will return once there's a better substrate for it to grow on.
From the local divers who are covering a huge area and not just, we've got specific timings that we're doing the eDNA analysis, they're in every day. Across the whole area. And we have found, for the first time, we've recorded stingrays in the area. That was that picture that I had. That's the last 2 years, and we haven't seen those for a couple of decades. I've certainly seen, when I've been out, and some of the other divers have certainly noticed that we've got a lot more starry smoothhounds. And before it was kind of only the small spotted cat shark. We've seen kind of bullhuss and sort of starry smoothhounds, so some of those large predators coming in. And I think Sussex Dolphin Project have kind of said that there seems to be more kind of marine mammals, particularly kind of seals and dolphins. And we've had bluefin tuna that we haven't seen for quite a long time in the last couple of years. So, we can't definitely say that's linked to the bylaw, but we didn't see it before. So more anecdotal than because we need more time to get that kind of recorded.
Hi, we have a question from someone attending online. So they say, do you see any potential for nature-inclusive design measures associated with energy projects, e.g. cables, contributing to the restoration of kelp? I've been asked that a few times, actually. I think I'm not the only one in the project that have been asked.
I think I don't necessarily think that pushing for kind of more of that, the kind of aquaculture is necessarily kind of the best move right now. I think I'd rather just leave it as it is. We're looking at kind of 5 to 10 years before we're expecting to see anything. It's been kind of 4 years. We'd rather see if we've got kind of natural regen at the moment before we start to look at kind of any other potential solutions. Yeah, sorry. I don't know who it was.
Thank you. Will Manning from EA and Flood and Coastal Risk Management side of things, and poster 16 for my broader work. But linking back to the earlier question about forward looks, and in the context of this kind of conference on seascapes and connectivity, does your monitoring include anything looking at like the energy reduction approaching the shoreline based on the way that that functional and kind of build of kelp?
I mean, at the moment, well, we have seen kind of changes in some of the macroalgae, but we haven't seen massive increases. There's been changes in the kelp. I think if you wanted to look at reductions in wave energy, you would need to have a much larger area that had been recovered. So then you're talking about kind of wave buoys and that kind of, which you could put micro buoys in. We have actually done that in one of the other projects. Actually in Sussex as well, but not linked to the kelp. Yeah, so we would be interested in looking at that, but at the moment, I don't think there's certainly not enough. There hasn't been enough kind of recovery of any of those large macroalgae to actually make a difference. So no, not as yet.
Thank you very much. Our next speaker is unfortunately had to pull out at the last minute, but has been able to send us this presentation, which we are delighted about. This is from Bryan DeAngelis, who is a senior scientist at lead scientist, I think, at the Nature Conservancy, based in the United States, and he's going to provide us a perspective on the last 50 years of native oyster restoration and what has made it go to scale there. So I'm really looking forward to sharing his perspectives.
Greetings, Seascape Symposium. My name is Bryan DeAngelis, and I'm a lead scientist with the Nature Conservancy. I'm deeply sorry I was not able to be there with you in person, but I'm so thankful to Dr. Ermgassen for allowing me to share this presentation with you today, entitled Scaling Up, the Evolution and Global Context of Oyster Restoration in the United States. So, let us first set the context of where we are with oyster restoration in the United States today. Recently, Elliott Hall and I published a study where we estimate the oyster reef restoration market in the U.S. to be about $70 to $90 million per year, with about 60 to 70 million of that going to in-water projects, shown with the dark blue on the left. To reach this estimate, we looked to 5 years of data from 2016 to 2021 and took annual averages. So one important note, all this data was collected before the bipartisan infrastructure law and the Inflation Reduction Act legislation from the Biden administration, both of which provided significant funding to habitat restoration. So presumably, these annual averages are currently inflated and potentially inflated by a lot. For example, I will reference a project later in my talk today, which was funded for $10 million for oyster restoration through the funding offered by this legislation. So my point here is that there is currently substantial funding towards restoration in the U.S. that is happening presently, but has not yet been fully captured in the data. What exactly do we mean by scale when it comes to oyster restoration projects? In the market analysis study I just referenced, we gave this some thought in the relative context of project maturity and how that varied state by state in the United States. Here, we defined the degree of project maturity as being pilot stage in the early phases, where small pilot projects are being done, often research focused, to prove concepts and build confidence. Often, there is limited coordination between different stakeholders at this stage. From there, the second phase is the scale-up phase, where states tend to get more of a mix of pilot and small to medium-sized projects, and funding variety starts to become more realized, with a mix of both philanthropic funding, research-based funding, and state and federal government funding. Large scale and full maturity is really only differentiated by mature programs having fully coordinated, consistent funding for long-term restoration and management programs. And despite an often common misconception, all the US states are far from the same. In fact, when it comes to oyster restoration, the states are at various stages of restoration maturity. That being said, if we look at the states that fall in the intermediate to larger scaled projects, we can see that it's starting to be more of the norm than the exception to be in that phase. And what I find most interesting and exciting is that projects that we would have once called groundbreaking and everyone would be aware of them from coast to coast now barely even make a splash. For example, these states in the still early but rising part of the curve, such as New Hampshire, that program has successfully restored more than 28 acres or 11 hectares of reef and 3.5 million oysters to the system since 2009, and are now averaging about 5 acres and 1 million oysters annually. Or in Washington, their Liberty Bay project is approaching the 50-acre mark, and their recent Dyes Inlet project is a 20-acre project constructed last year. Or in Louisiana, they're just finishing 4 consecutive miles of shoreline oyster reef restoration in Calcasieu Lake, just one of several projects of similar size in the Gulf of Mexico that receive little fanfare and few people even know about. However, the one that many of you have probably heard about is the Piankatank River project in Virginia, which completed nearly 500 acres as part of the world's largest oyster reef restoration, which is the restoration of over 2,300 acres across 10 tributaries in the Chesapeake Bay. In fact, the Chesapeake Bay oyster restoration effort is such a flagship effort in the United States that a few years ago, we included it as a case study in a paper we wrote that explored what the factors were that led to large-scale restoration successes. I'm not going to review that paper in detail here today, but in summary, the results indicated that across different habitat types, including salt marsh, eelgrass, and oyster, common themes included a recognizable ecological crisis with a corresponding public demand for action that was followed by political response, which catalyzed the development of estuary-level recovery plans, and then the development of those comprehensive plans for action that included clear and measurable goals, and then, of course, funding provided to implement the plans through various mechanisms. But while that paper explored commonalities across existing case studies, it didn't actually explore the evolution of ecological restoration, particularly shellfish and oyster restoration in the US. In fact, to the best of my knowledge, nobody really has. Obviously, the progression and progress of oyster restoration in the US does not have a direct and clear cause and effect, and trying to hindcast back to identify those cause and effects is nearly impossible. However, I am confident of some key enabling factors that greatly contributed to the evolution of where oyster restoration is in the US today. The factors I present here are in no way meant to suggest they were the only factors. However, those I present are unique attributes that I'm confident help move the needle in the US and align with what we saw here in this study when we downscaled our view into individual programs at the case study level. The first factor I think is worth mentioning dates back several decades and is deeply rooted in a long-standing American tradition. That is, resolving disputes through litigation. As one of the initial drivers of oyster habitat restoration was a government legislated requirement to restore the public resources injured by discrete environmental incidences such as chemical or oil spills. The initial legislation was described in the Comprehensive Environmental Response Cleanup and Liability Act, or CERCLA, of 1980, and the Oil Pollution Act later in 1990. For each incident addressed under such legislation, the damage first needs to be quantified prior to designing restoration to make the community whole. These laws help develop both the practice of oyster restoration and the initial methods to measure the ecosystem services from oyster habitat as an additional service to be accounted for. This legislation continues to influence restoration today in almost every coastal state in the US, including, of course, the well-known Deepwater Horizon spill that happened in 2010, in which several billions of dollars of habitat restoration is being implemented as we speak. Federal agencies supporting and funding coastal habitat restoration has been another critical factor in the scaling of oyster restoration in the US. The NOAA Restoration Center was formally established in 1991, shortly after the Oil Pollution Act of 1990, to lead habitat restoration efforts and support natural resource damage assessment. As a result, the US now had an entire line office within the Department of Commerce with the specific mission to restore coastal, marine, and migratory fish habitats to sustain resilient ecosystems and communities, and operating not only on response funds from oil and chemical spills, but from the annual budgets appropriated by Congress. We know from Berzosa Hernandez et al.'s work that oyster restoration started in the 1990s, but there was a significant inflection point around the year 2000. And among other factors, I think a major driver of that inflection point was NOAA's community-based restoration program. This graph shows NOAA's community-based restoration oyster restoration funded projects from 2000 to 2012 for both number of projects and acreage on the two y-axes. This program is operated with federally appropriated dollars, not dollars from legal settlements that I was referring to before. You can see the first decade or so that the number of restoration projects funded in the US not only grew in number, but also in total acreages. Another critical inflection point worth noting is the spike you see in 2009 in both number of projects and size of projects. This spike reflects the funding from the American Recovery and Reinvestment Act, which in the world of habitat restoration pushed the community to identify and implement projects that had previously been unattempted. This included, among many other projects in the US, 78 acres in North Carolina's Pamlico Sound, or the Nature Conservancy's 101,000 Restore Coastal Alabama project, which intended to build 100 miles of oyster reef to create the conditions needed to plant, support, and promote more than 1,000 acres of coastal marsh and seagrass. And while NOAA has played an outsized role, that was not the only federal agency that has been supporting oyster restoration. Other agencies have included the Environmental Protection Agency, United States Fish and Wildlife, the U.S. Army Corps of Engineers, and others. Even the Natural Resource Conservation Service, an office within the U.S. Department of Agriculture, has funded projects because oyster aquaculture is considered farming under the definition of some of their environmental programs, and we have been able to tap into that to fund restoration conducted by the oyster farmers. However, you can see from this graph, which is federally funded estuarine restoration projects from 2006 to 2015, that oyster restoration was only second behind tidal wetlands in terms of number of projects funded by federal agencies. However, the federal agencies were just a necessary catalyst for growth of the oyster reef restoration industry, because for the number of projects, size, and complexity of projects to grow, you needed on-the-ground practitioners and project implementers to build those projects. And here's where I must highlight the role of the Nature Conservancy. So yes, while I am clearly biased, I do genuinely believe that in the days of the early 2000s, the Nature Conservancy's very deliberate and targeted focus on growing oyster reef restoration across the country overall had an outsized role in how the industry scaled over the years. Because over the years, TNC has deliberately focused on improving the enabling conditions to build larger and more complex projects, often at the municipal and state level, as in the US, the policies and regulatory frameworks are often different state by state. But generally, our efforts focused on developing multiple on-the-ground partners to have the capacity and, most importantly, the confidence to build larger and more complex projects. and we focused on the lowering the activation energy barriers that often impede projects such as permitting and appropriate site selection. And one that I want to point out specifically is addressing key research questions. This is an area that TNC put significant focus on, but importantly, not just on academic research questions, but more specifically, using science to inform the application of oyster restoration. And here, I must stop and point out that our symposium's very own Dr. Philine zu Ermgassen was instrumental in producing a vast quantity of this science that helped build and advance our community of practice. There are far too many products to list, but the examples I think that are most relevant to this presentation are those science products that were explicitly developed to inform restoration practitioners to be able to use science and practice to advance the implementation of their projects. These include, from the very early days, the first Practitioners and Best Practices Guide, the very well-known Shellfish Reefs at Risk Report, Best Practices for the Interstate Shellfish Sanitation Commission, Philine's large body of work which documented the historical ecology and massive loss of both habitat and associated ecosystem services across the U.S., a monitoring and evaluation manual which systematized how all restoration projects were monitored in a standardized way across the entire country, more science that started to quantify the fisheries and productivity from these habitats, and then a manager's guide about how to actually set restoration targets based on these quantifications of ecosystem services, and more recently, a revised and updated best practices guide for practitioners, and new scientific publications that are based on setting large-scale restoration targets based on ecosystem services. And this is just a small fraction of the products we've developed. But the theme here is consistent. All of our science-based products are started with a very deliberate intention. Provide resource managers, funders, and practitioners the science-based information they need to move and advance projects in size, scale, and complexity. The next factor I'll introduce is motivation to restore places, not projects. In the context of today's conversation, the word scale should be defined by what society wants back from the habitat. In other words, how much habitat is enough to get the desired amount of a particular service. Referring back to the Chesapeake Bay example I referenced earlier, the critical thing about that case wasn't the size of the projects. It was that they were setting restoration goals at the level of entire tributaries, not individual projects. This idea, understanding what your ecosystem service motivations are for restoring the habitat, whether it be fisheries productivity, denitrification, sediment stabilization, or other, and then determining how much of the habitat is required to deliver that degree of ecosystem service is where the Nature Conservancy has spent a significant amount of effort in messaging and lobbying for both practitioners and governments. And while I cannot claim we have reached this level of thinking and ambition in all places in the U.S., the progress we are making is exciting. For example, one place I have been working a lot in the past few years is the Florida's Pensacola Bay, a 233 square kilometer estuary in Florida's Panhandle region. For the past few years, TNC and the local estuary program have worked with the community to set large-scale estuary-level restoration goals for the entire bay. Through that science and community-led process, the community identified a goal of restoring 1,500 acres, or 607 hectares, of oyster habitat. All that planning and large-scale goal setting eventually led them to securing a $10 million award from NOAA's bipartisan infrastructure law to kickstart that initiative. Beyond the leveling up of ambition with examples like this, it's important to recognize the fundamental economic and efficiency benefits that are able to be capitalized on when restoration gets scaled to this degree. Because when we start to look at restoration at this scale, we can start to be more business-minded in how far our dollars go. For example, we can start to maximize several economies of scale on everything from engineering, design, materials procurement, and construction. This whole topic of improving economic performance, in other words, the cost of restoration, as we grow and scale projects, has been a major focus of my work lately. And although I don't have enough time to get into it now, if you're interested in it, I encourage you to check out this document I recently published and refer to the performance improvement strategies provided through scaling restoration. Despite everything I have discussed here today, I think the most important factor to growing restoration is a term I call socializing scale. And by that I mean, without someone or some entity constantly encouraging the community to push the envelope, we will forever be hamstrung by our own inherent characteristics as scientists to be risk adverse. As scientists, our inclination is to constantly feel like we still do not have enough information, because we, more than anyone else in the world, realize the true biological and ecological complexities of a project and how they change under different ecological context. Therefore, our inclination is to build another pilot project or test another variable. However, while we must always operate under the first principle of do no harm, I challenge the belief that we don't have enough information to start scaling our restoration projects to sizes that are ecologically relevant to society's demands. I feel this way because while there is much to learn, we know a lot, and there is enough science to act. Maybe more relevantly, restoration will always be an applied discipline where we will never learn faster through research than by doing. And that includes the variables inherent of projects growing in size and complexity. Our job as scientists is therefore not to restrict implementation of projects due to lack of science, but to ensure we always maximize learning and adaptive approaches by pinning monitoring and research to applied projects. And we must always consider the cost of unambitious or no action. Our coastal habitats are in a dire state and expected to decline even further with future impacts. There is a strong argument to make that our threshold and tolerance for risk should appropriately rise if the trade-off is an acceleration in the scale of restoration. Sorry I couldn't be there with you in person. I hope you enjoyed the presentation. Have a great symposium. Take care.
Thank you, Bryan, for that really engaging talk. And just to be clear, I am his biggest fan. We'd now like to finish off the habitats individual section. We're very pleased to be having Richard Unsworth speak to us today, coming from Swansea University, Project Seagrass, founder director, Seagrass man.
Thank you very much. It's a pleasure to be here. And I clearly didn't offend too many people last time because I've been invited back, so that's a good place to start. Today I wanted to give a talk about seagrass in the context of the broader coastal seascape, rather than just thinking of it as the one habitat, but how it exists across that seascape in different settings, and the different, I guess, challenges that we face in trying to bring back seagrass at a scale that's relevant, and that a whole lot of excellent speakers have referred to, that we need to think bigger, and therefore we need to face many of the difficulties in seagrass restoration that we're experiencing. And this second slide sort of reflects that difference here, where the first one is this sort of lovely picture that we all see of these amazing seagrass meadows, thick, full of life, really green. And the reality is that we spend a lot of time out in these muddy environments covered in all sorts of goo and stuck up to our waist. And we don't often recognize that seagrass is this sort of far more extensive bigger habitat across the seascape. But for me, the elephant in the room around seagrass restoration remains the fact that there are very, very high levels of failure. And whilst I've got this number for seagrass, I'm sure there are pretty similar numbers for oyster restoration, for mangrove restoration, for coral reef restoration, and the list goes on. It's difficult, it's challenging, and largely marine restoration as a concept is actually very new. So whilst people have been planting forests and conducting agriculture for thousands of years, we're really in the such early days of trying to think about rewilding, rehabiting our marine environment. And today I wanted to talk about 5 key factors that I see as needing to push forward to actually think about how we can improve restoration. And as Philine talked about earlier, scale is one of those. I'm not going to go into that today, but there's far more parts to that puzzle that we need to think about. And firstly, I wanted to talk about the setting of seagrass in the temperate seascape. And whether it's this example I'm referring to here is Zostra marina, it's kind of phenotypically adapted to different environments. With some environmental settings, you have different species adapting to different niches. Here we've got one species adapting to multiple niches. And these kind of differences we see in the tropics as well as the temperate environment. But what we're seeing here is that, yes, we get that lovely picture, which is the bottom left square. That's Portland Line on the North Wales coast. It's a fantastic dive. I can spend hours there under the water with a camera, finding all sorts of amazing little creatures, highlight, really lush green seagrass. And that's very different to a muddy intertidal seagrass meadow hiding up in a channel in a salt marsh. It's again very, very different to seagrass on an offshore plateau at depth off the Isles of Jersey. And again, it's very, very different to this meadow here on the top right, which is in just outside of Cardiff Bay. You can see the remnants of one of the bricks from the old harbour wall. That's about 3 or 4 meters from the upper shore, and that's exposed for hours on end every day. Even on a neap tide, it's exposed, but there's a tiny bit of water that means it doesn't desiccate and it survives. You also get seagrasses living in these sort of weird lagoon environments where salinity can be really low. Nutrients can be very high. There's very little water movement. And as Martin was talking about earlier, they're places where actually they're really great for settling of particulates and therefore accumulation of carbon. So all across that seascape, from the estuaries to the lagoons, to the islands, to the reefs, we have seagrasses. And they're all living there in those different environments. So we're not dealing with one seagrass species or habitat across that coastal seascape. We're dealing with multiple different settings. And that's why we need to rethink some of the aspects of how we're dealing with restoration in this coastal seascape to recognise those differences. We've actually when I say the word we, that's the royal we, and this was actually my MRes student. I didn't actually go to most of these sites. I helped him a couple of times. But my MRes student, Manning Hope, visited 16 seagrass meadows all around the UK. and looked at the biodiversity of the epifaunal communities living on that seagrass. It built on a method that we used in a program called the Oyster Experimental Network across the Northern Hemisphere, but took a zoomed-in approach to just looking at the UK. And we also looked at the seagrass, the condition of that seagrass, the nutrient status, all sorts of different parts of it, and began to see that there were big differences in the nutrients that were present in those seagrasses between those different environments. The C to N ratio in the plants is a very good indicator of the amount of light available to that plant to photosynthesize. So actually, it's not rocket science, but actually, clearly we're seeing high turbidity environments in those estuaries, in the coastal and the island environments, we're seeing much clearer water. And that has big influences for how we might think about going about restoration. And we saw differences in the amount of seagrass, we saw differences in the abundance of the animal communities, the richness, and their functional traits. So these sorts of things begin to cascade as to how we might consider rebuilding these marine habitats. And as part of a bigger survey, we've also looked at the nutrient status of seagrasses all around the UK. And some of these places are highly eutrophied. They're very, very nutrient rich. And that's actually massively influencing the viability of the seagrass in that location, but also the status of those that are present there. So where we get low nutrients, we get higher density seagrass. And what we're seeing by linking some of this data together is that there is a key relationship between the abundance, the species that are present in that seagrass, the epifaunal community, so things like isopods, small gastropods, hydrobia, things like that, and the biomass of the seagrass that's present. And that's being also modified by the amount of nutrients and the environmental conditions that are present in that seagrass. So broadly, what we're seeing across the coastal seascape is that there are a whole series of modifying factors that are influencing how we can go about seagrass restoration. It's obvious that like further up estuaries, we're going to have differences in salinity. We've got very big differences in the amount of nutrients we might expect in the Milford Haven waterway high up the estuary to the Isles of Scilly. And cascading to all these differences in fauna, we have different communities of animals that are predating upon that, different food webs that we don't really understand, that are influencing that whole bigger picture. And they're really, really important because a key part of the functioning of a seagrass meadow depends upon the epiphytes that grow in that seagrass community on those plants. And if there are not animals to graze that floral community, those epiphytes, then the seagrass becomes suffocated. So you're influencing the resilience of the system when there's differences in the amount of organisms, the species richness, the abundance of those animals that are living on the seagrass. And we're always considering seagrass restoration as one simple concept, but it's far, far removed from that. And it's very difficult to talk to a regulator to actually say, well, we want to do this method because it's in this environment. And often we don't really understand those rules. So we're guessing, and we're often second guessing as to what's right. But we need to understand this variability to think about what are those rules of engagement, because it's fabulous seeing all those reports and those technical capacity coming out of TNC. It's amazing to see that. We're so far behind that from a seagrass perspective because our understanding of many of these different factors in that coastal seascape and our ability to apply them is just not present. We've not done the the basic ecology, and it feels like we're often trying to run before we can even crawl. But there are also these feedbacks in seagrass systems, and some of those are natural feedbacks that are in balance, and often many of these feedbacks get out of balance, and that becomes problematic. Geese graze seagrass, and that seagrass needs to be resilient enough to respond to it. And in a natural scenario, that's possible. We plant some seagrass in North Wales on the Phillip Peninsula. It's growing really well. We think we've cracked it. It's brilliant. Geese come in and destroy it. It's because possibly we haven't done it at a big enough scale. But there's these parts of it that we need to think more about. And that's really, really important because those feedbacks are actually largely out of balance. You know, it was interesting hearing Iris talking earlier about that physical environment. And ultimately, it's that physical environment that we've completely and utterly decimated in the European coastal seascape, largely the whole temperate seascape. You know, we've destroyed whole estuaries. Philine talked about the decimation of the oysters, but we've not just done that. We've built barrages across many estuaries. We've removed the salt marsh. We've made sediments more mobile. There are places that we've got no understanding of whether seagrass was ever there, but these places have never had seagrass in living memory, but they're all places where we changed the fundamental structure of the natural environment. And if we want to think about recreating habitat, we need to think about the feedbacks that come from all these activities that we've done in the coastal environment to change the physical structure. And largely that's environments where we have unstable sediments that are awash, that they're moving around estuaries, coastal seascapes. That means actually you can't suddenly put a little plant back into a seascape because there's some sediment that's just going to swamp it on the next tidal movement. And these feedbacks are critical. And, you know, what Iris was talking about, that longer understanding of the physical environment, that's what we need to think about in order to have a better understanding of how and where we can restore. And that also then cascades to how we approach the restoration, because we can't just say that an environment is too unstable, therefore we can't actually restore in it. We're too much up S Creek to take that approach, and I think we need the ambition, and therefore we need to learn to manage and control feedbacks. In parts of Northern Europe, they've used sand capping, and I think they're about to do that up in Loch Cradenish in Scotland. They're using sand capping to control fine sediment resuspension. There are methods that are being used to control hydrodynamics, so you can actually facilitate seedlings to get to a certain size where they're actually able to withstand physical impacts. We need to learn to control these feedbacks and think how we can actually progress in terms of success. We also need to think about communities, and all too often in restoration we don't bring the community with us, and it was kind of nice hearing that talk about the oysters in the US and how, you know, community practitioners are helping people along that journey. And in some places we are seeing that, and there's great momentum in that scenario, but sometimes those communities aren't engaged and they're not actually helping facilitate restoration at scale. And we need to think about how we can do that. And that's not just about seagrass, it's about oyster restoration, it's about salt marsh restoration. If you bring communities along on that journey, then they want to be with you, and it's encouraging seeing groups starting to do this with salt marsh. Angus finally getting volunteers out onto a muddy seascape. It's great to see, and we have to do this more and more to get people involved with all types of restoration, so they can be on the journey with us and be part of putting that pressure onto government, to funders, to actually facilitate restoration at scale. But lastly, I also wanted to touch on licensing, because it is my pet hate topic, but it's something that remains a consistent problem for marine restoration. And I recently reached out to a whole group of scientists all around the world involved in marine restoration, some of them in this room. And what's clear is that most of these people have examples where restoration is being hampered by licensing problems. It's leading to all sorts of weird and wonderful scenarios that are not helping nature recovery. They're not helping us actually rebuild marine life. And ultimately, they're creating a bottleneck. And this is leading to suboptimal projects, reduced innovation, poor project design, increased project costs, and ultimately the loser is the natural environment. And we need to think bigger about how we can overcome this, because we don't have time, and it becomes an increasing frustration. But lastly, I wanted to actually talk about communities learning together. And I know that this is a great place that everyone's coming together and actually trying to push forward restoration in the coastal seascape. And we have to do that together. And the seagrass community is not doing that. And we need to be better at sharing our successes, our failures, and actually logging where we're doing restoration. And my last slides are about a platform that we're about to launch this Sunday to coincide with the UN Ocean Conference, called Seagrass Restorer, where we're hoping to get organizations, communities, universities, at the very least, just logging where they're doing restoration. And at a recent conference, there was a great example where a group in France had picked up just some basic information about a restoration project that happened in the 1980s, which had been largely considered to have failed. They had very little information about it, but they found it, and they actually discovered that 40 years later, actually, there's a flourishing seagrass meadow. And that's because someone recorded it, and we don't record, we don't share, and no one learns. And that's what we're trying to do here, is push that forward with the launch of Seagrass Restorer. And thank you very much.
Thank you very much for that talk, Richard. Really appreciate it.
Hi, thanks, Richard. Roanna Walton from UNEP WCMC. Just really interested in the seagrassrestorer.org, and just wondering, one of the challenges often that's faced is the engagement of communities, practitioners, researchers to upload that data into the platform. It's not just getting the platform, it's the interaction, engagement. I'm just wondering what steps you've put in place or what your plan is going forward to get that engagement.
Currently, we're trying to work with lots of different funders to encourage them. One of the big parts of it, we've co-designed it with a whole load of academic institutes all around the world who are involved with restoration projects. And we're trying to obviously push it and spread the word through different networks. But by trying to get lots of bigger organizations involved, we're trying to get them to walk the walk, and then others will follow. But I think one of the key things is that we've got a very, very low threshold of what we want partners to input. It's better to have some data than no data. And if someone can say that we planted some seagrass, it was Oyster mariner there, that'll do. And that means that in 20 years' time, a PhD student could go around and find all those locations and find Did it actually work? And, you know, having that level of information is something that we don't have. We've got no idea where the UK's restoration is happening, Europe's restoration, we don't know. And it falls then down to those who academically report things, and most people academically report successes and not failures. So we have a skewed view.
Thank you. Hello, Richard. Thank you for that. It was a really interesting talk. I'm Sally Little from NTU. So just a quick question. You said the 63% failure rate for seagrass restoration. If I was going to ask you very quickly what are the main reasons for the failure, what would you say? I'm going to say water quality.
But it's fundamentally about the environment. It's understanding the environment and whether it's not just whether the environment's suitable, but whether the method is suitable for that environment and at the right scale. And I think that's critical. And if you're dealing with a highly mobile system, that might actually not be helpful, for instance, planting little seedlings or little seeds, because they're just going to be knocked out, and therefore you might need to use transplanting techniques, and those transplants might need to be heavily anchored down.
Okay, so a lack of knowledge, essentially,
Yes.
of the sites. Brilliant. Thank you.
Right, wonderful. Thank you so much. Really appreciate that. Lovely.